So we are going to learn the vector equation of the line. Here's the idea. You've got a line. This is the line. It's going through R, it's going through A, it's going through C. You have position vectors based on your origin. So I have a position vector A, a position vector R, a position vector C. We can say that the direction of our blue line is the same direction as going from A to C. Does that make sense? Because A and C are both on that line, so we have a direction vector which, using what we know about vectors, you can go from A to C. Well, that would be, if I wanted to start at A and get to C, I could do that by first going negative A and then going positive C, or C minus A. What we're going to call that red line is our direction vector. And with an equation of a line, we had the direction in the past with y equals mx plus b as our slope. Our slope sort of told us go up 2 over 1, up 2 over 1. That sort of told us a direction. Now we have a direction vector that's telling us the direction. R is any point on our line. So this vector R is like any point on that line. And the vector R, or any vector, can be gotten by starting with a random point. So here we're going to label some of these things. We've already talked about B. That's your C minus A. This is what we're going to call our direction vector. We're going to think of it like our slope from our y equals mx plus b. Now, with y equals mx plus b, B was a specific point. It was always your y-intercept. With the vector equation of a line, the A is any point. It doesn't matter which point you choose. So A is any point, and R represents all points on the line. Any random point. Maybe that's even good because it's R for random point. It's any random point on the line. Any point whatsoever. So if we think about what this means, it says that you can get to any point on the line by first going to A. So if I start here and I go to A, and then if I wanted to get to R, I would have to go some portion of the way from A to C. In this case, it kind of looks like maybe 2/5 of the way. And so then my T would be 2/5 to find that particular R. If I wanted to find another point R on the line, maybe this was the point R, I could do that by going to A, and then this time I'd have to go along AC a little bit more than 1. If R was over here, I could go to A, and then I could get to that point by doing a negative of the direction from A to C and some proportion of it. And if I include all possible values of T, I will draw all possible values of R, and all those points together make up a line. And that's why this is a vector form of y equals mx plus b. What's the nice thing about this is it's going to allow us a way to not only talk about 2 dimensions and stuff that we already know, but also talk about lines in 3 dimensions. because we don't have really a language yet for slope of 3 dimensions. In 2 dimensions, it worked out as a nice fraction. In 3 dimensions, do you have like a fraction with 2 lines? I don't know how you would write it. So it doesn't quite work well for us. But the vectors are going to work really well. So we can write this equation in a bunch of different forms. Okay? So this is right here. This is r equals a plus t times b, where b is our direction vector, a is any point, and r stands for all points on that line. The parametric form says if you think about, and this is in 2 dimensions, if you think about x coordinates and y coordinates, what we can do is write out a specific equation for your x coordinate. Your x coordinate, and I'll just do the highlighter here, your x coordinate is going to be a1 plus b times t. And that is one equation. Your y coordinate is going to be a2 plus t times b2. And this is called the parametric form of the equation of the line. The last form is if you take the parametric forms and you rearrange them to solve for t. So I would subtract a1, then divide by b1, or subtract a2 and divide by b2. Since I solved for t in both of those, I could equate those 2 equations, and this is called the Cartesian form of the line. Each of these forms is going to be helpful. So here's our first example. We want our vector equation of our line passing through a 2, 5 and parallel to 3, -4. If it's parallel to that, then 3, -4 is going to be our direction vector. And our equation of a line is always a random point. Well, we know it goes through 2, 5, plus a scalar, and then our direction vector. So writing an equation of a line in vector form is always very quick, because you just need any point and the direction it's going in. In that way, it's probably most similar to, remember the point-slope form, right? You needed any point and the slope. This is the same thing. Instead of a slope, we have a direction vector, and then any point. So then taking this, we can write our parametric form, where you look at your x coordinates and you look at your y coordinates. And finally, our Cartesian form, the Cartesian form is where you say, if I solve for t, in my first equation, I would subtract 2, then divide by 3. In my second equation, I'd subtract 5, and then divide by -4. And then equating those 2, that becomes your Cartesian form. This is what this question asked for. I want to connect to you what this is actually meaning to your math from before, especially the Cartesian form. Notice the t is gone. The vectors are gone. We just have x's and y's. If you multiplied that out, you would get, like cross multiply here, I'm going to get -4x plus 8 equals 3y minus 15. If I move the 15 over, I'd have -4x plus 23 equals 3y. And y is equal to -4/3 x plus 23 over 3. Not very nice numbers, right? If we think about this going back to y equals mx plus b. We know that our original equation went through the point 2, 5. There's our point. And it tells us that it's parallel to the vector 3 to the right, 4 down. If you think about that, going 3 to the right, 4 down, can you see that that would have a slope of negative 4/3? Using y equals mx plus b. I know that when x is 2, y is 5. I know my slope is negative 4/3. If I multiply this out, I'm going to get 5 equals negative 8/3 plus b. Add 8/3 to the other side. I get 23 over 3 equals b. And if I wrote that out in y equals mx plus b form, it's the same equation that I get by rearranging my Cartesian form. So you can take your vector form, change it to parametric, change it to Cartesian, and you can get back to y equals mx plus b that you had before. So here's another one. We're going to find a vector equation of a line. No, this is the same. No, this is a different one. Perpendicular. Still same point, 2, 5, but it's perpendicular to 3j. So if 3, 1, 3i plus j is that vector, and we want to be perpendicular, then our direction vector will be 1, 3, and you need to make one of them negative. And it doesn't matter which one you make negative. It's up to you. So then our vector equation of our line, any point 2, 5 plus t, 1, negative 3. Our parametric forms, our x-coordinate is 2 plus t. Our y-coordinate is 5 minus 3t. And our Cartesian forms, if we solve for t, we'd have x minus 2 is equal to y minus 5 over negative 3. So how can we make these more difficult? This was a little bit more difficult because it took us some time to find our direction vector. But again, just like with your equation of a line, you needed point and a slope. With a vector equation, you need the same thing. You need point and a direction vector. Basically the same ideas that you had for lines way back in grade 10. So I want you to write all the forms for this one. But this time, the direction vector isn't given. They give you 2 points, but they don't give you direction vector. Until you get really familiar with vectors, for finding direction vectors, A, B, draw a picture. Draw your origins so you can think about your position vectors. If I started at A and I wanted to get to B and I wanted to use my position vectors, can you see that you could go negative A and then plus B? As you get better at these, you'll be able to just directly say that AB is equal to B minus A. And if I know that B is 5, 8 minus A, which is 1, 4, I'm going to get my direction vector to be 4, 4. So now what is my vector equation of my line? I could choose either 1, 4, or 5, 8. It doesn't matter which of those two you put here, because that's any point on the line. Plus t, and our direction vector is 4, 4. And with our direction vector, just like slopes, can you see that that slope is really 4 over 4? Could you reduce that to 1 over 1? Yes. So you could have also written for your direction vector any multiple of that. So if you had 1, 1, or 2, 2, or 3, 3, that would be right as well. But then from this, we can say, what is our parametric equation? Well, our x-coordinate is going to be 1 plus 4t. Our y-coordinate is 4 plus 4t. And our Cartesian forms, solving for t in both of them, and then making them equal. So then we can have some fun with 3 dimensions. Going from P to Q will be Q minus P, or 2, 0, negative 4 minus 1, 5, 3. There's our direction vector. So then our equation of our line in 3 dimensions, choose either one of those points. And then add your direction vector. Now, if a point is on that line, then there has to be a value of t that makes that work. So in other words, if we're wondering if negative 1, 3, 5, that is a random point that we're saying, is it on the line? This is our question mark. Then there would have to be a t value that makes that work. And this is where your parametric equations are going to come into play. Because if I look at my x-coordinates, it's saying with my x-coordinates that negative 1 would have to equal 1 plus t. If that's the case, can you see that t would have to be negative 2? Yes. Yes. Thank you. There we go. So there's my parametric equation for x. If I look at my parametric equation for y, I'd have 3 equals 5 minus 5t. If you solved for this, t would equal 2/5. So I already know my answer to this question. I don't even have to do the third one. My answer is going to be no. Because if that point is on the line, then there has to exist a scalar t that makes that work.
Instead of just solving for t, like, would it be possible just to put t back into y?
Yes, you could also, once you get t is negative 2, you could plug the negative 2 in and see if it doesn't match with all the points. That's basically doing the same thing. So yeah, and to make matters worse, if we had done the last coordinate and solved for t in that one, we get negative 2/7. So all 3 of them don't match. How about the point 3, negative 5, 5? What's your guess on this one? Yes or no? Just gut feeling. Sure. Okay, let's try it. So looking at our x, we'd have 3 is equal to 1 plus t, which would imply that t is equal to 2. Our y value, negative 5, is equal to 5 minus 5t. Solving for that, t is equal to 2. Things are looking good. And 5 is equal to 3 minus 7t. Solving for that, oops, t is equal to negative 2/7. Oh, doesn't work. This is me enjoying messing a little bit with you, right? I asked your gut reaction because what do teachers always do? They always have one example that doesn't work, one example that works. Right? Are you sort of used to that? So I thought, mess with that a little bit. Right? Wow. It's too much right before spring break, I'm sorry. So yeah, all three of them would have to be the same in order for you to say, yes, that point is on the line. But in this case, it's not. Here we have another vector equation line. It's written a little bit differently. I could rewrite this by saying my vector r is equal to, the random point is 3 over 5. My scalar is t. My direction vector is 2, negative 5. Do you remember how to find unit vectors? No. That's okay. But it's there because it's something I want to really point out in this unit. This unit is not hard, but it can be a unit that really gets you because it's easy to forget how to do things. So you have to study. You have to know this unit well, and you will do well in this unit. But if you don't study and just think this unit is easy, you will find that this unit really is mean to you. So yeah, unit vector. What is a unit vector? It is a vector in the same direction, but of length 1. So first of all, we have to make sure we recognize we've got two vectors here. That's our first choice. Which one of those is the direction vector? The 3, 5 or the 2, negative 5? 2, negative 5. If I find the length of the 2, negative 5, that'll be the square root of 2 squared plus negative 5 squared. It'll be the square root of 29. That's how long that vector is. So my unit vector, I would have to divide by that to get my unit vector. And you could distribute that 1 over root 29 if you would like, or leave it. Find the Cartesian form. In order to find the Cartesian form, we need our parametric form first, our x-coordinate, our y-coordinate, and then we could solve for t in both of them. And we have our Cartesian form. Question number 6 is a very typical 7-mark vector question. So we get two equations of lines. We have two different scalars because they're two equations. So we've got s and t. We want to find the position vector of their common point. So the first thing that I find is useful for both of these, so we've got RL, write it out 5, 3, 0 plus S, negative 4, 1, 2. And Rm goes through negative 3, 7, 6 plus T, negative 4, negative 1, 0. In particular, I want you to think about the zeros, because I included zeros in this one for that purpose. In the first one, can you see that your original point doesn't have a z coordinate? Because with your k, there's just a 2s. And that s is getting multiplied by 2, but there's no number multiplied in front. And in your second one, there's a 0 here in the direction vector because there's no t with your k value. Your z is always 6. So find the position vector of their common point. What we're going to do here is we're going to look at each of our parametric equations. So here we'd have 5 minus 4s. For y, it would be 3 plus s. And for z, it's 2s. And in green, my other line, I'm going to have negative 3 minus 4t, 7 minus t, and z is always 6. With this information, what you're going to do is you're going to look at your x coordinates, y coordinates, and z coordinates, and our plan is to solve for s and to solve for t. Now, in this situation, there's going to be one variable that's going to be the easiest to solve for. Looking at your equations, what can you tell right away? S is going to be 3. So this is an easier one because we can right away tell that s is equal to 3. If in this one you couldn't tell something easily, you're going to have to solve a system of equations. You could have made your x1 here one system of equations, your y1 here another system of equations. Those systems of equations would look as follows. I'll do it in a different color here. Would you agree that 5 minus 4s, if the x coordinate is in common, would have to equal negative 3 minus 4t? That could be one equation using two variables, s and t. And if I equated my y coordinates, I have 3 plus s is equal to 7 minus t. That could be a second equation with two unknowns. Then you could use substitution or elimination to solve. But in this example, it was extra easy because they told us that s was 3. Well, they basically told us that s is 3 from the z coordinate. Once we know s is 3, you could use either of those other two equations and figure it out. I'm going to use equation 2. If I use equation 2 and I put s is 3, then I would have 3 plus 3 has to equal 7 minus t. Solving for this, we get t is equal to 1. If there's a point in common, that means when I plug in 3 for s, I should get the same point as when I plug in 1 for t. It's not enough just to plug in one value and not check the other one, because there's going to be some times that you'll have two lines that cross but never touch. But in this case, if I plug in 3 for s on my line RL, I get 5 minus 4, negative 7. 3 plus 3, 6. 0 plus 6, 6. On my line RM, if I plug in t equals 1, and I'll just write here s equals 3. If I plug in t equals 1, I get negative 7, 6, 6. So what do I know? So negative 7, 6, 6 is the point on both lines. It's the common point. So can you visualize this? Probably not very well, but can you kind of visualize it? Can you imagine in 3 dimensions 2 lines? And can you imagine those 2 lines intersecting? Right? If you were looking at it and could imagine in 3 dimensions, you have one line here, maybe another line there. They intersect at a point. But this is in 3 dimensions. That's a 2-dimensional picture. Kind of imagine that in 3 dimensions. You can have a line going that way and another line going that way. They intersect here at some point. And that point where they intersect is at negative 7, 6, 6. Now, part B, what is the angle between those 2 lines in 3 dimensions? Well, what did we know, or what did we do with angles the other day? We rearranged our dot product formula, and we had that cos of theta was always equal to the dot product between 2 vectors divided by the length of those 2 vectors. Earlier I said this whole question was out of 7 marks. I lied. Sometimes this question alone is 7 marks. And it's not hard. But you get 2 marks for choosing the right vectors to use. So when we're looking at our 2 equations, RL and RM, and I want to find the angle between those, of those 4 vectors, which do I choose? Just randomly, 4 choose 2, that's 6 possibilities. You got a 1 in 6 chance. Should we do that? Or which would be, why not? Which 2 vectors? The direction vectors. So we need to choose our direction vectors from both of these. Once we've chosen our direction vectors, so choosing the right vectors is the first thing. Then we need to find the dot product in between them. How do we find the dot product? Multiply each corresponding value. So I'll write it out here. You would have negative 4 times negative 4 plus 1 and negative 1 plus 2 and 0. That's your dot product. Then we need to find the length of u and the length of v. So with negative 4, 1, 2, that'll be 16 plus 1 plus 4. I don't need absolute values there anymore, because that's the length of one of them. And the length of the other one would be negative 4 squared, still positive 16, plus 1 plus 0 squared is 0. So we get that cos of theta is equal to 16 minus 115 over the square root of 21 times the square root of 17. We go to our calculator. It doesn't matter if you answer in radians or degrees. Sometimes they'll say, for the most part, if they don't, why not use degrees? Because you probably can visualize it a little bit better. And if I write 15 divided by the square root 21 times the square root of 17, cos inverse of that gives me an angle of approximately 37.5 degrees. And again, I like to think back to what we just did relatively, relatively easily. We had two lines in 3 dimensions, which is hard to draw on paper to begin with. We found out where they intersected, and we're able to say the angle between them and what that's going to look like. Now, since most of our life we live in 3 dimensions, this has more applications to stuff that is on paper. I mean, on paper you can say, well, that's people driving on roads, and this is airplanes flying in the sky, right? Because it's not like on a road you're like, oh, I'm going to hit that car, but if I just go up a little bit, I'll be able to go over him. That would be, we can't do that yet, right? But this is 3-dimensional stuff, so you've got all sorts of applications for this.